All right, in this exercise, we have like a mobile that's hanging here. It has a bunch of fish on it, and we're given the weight of a fish B here. That's 27 ounces, and we are asked to determine what need to be the weights of the other fish A, C, and D in order for the mobile to be balanced. So and it says that these crossbars here assume that they have negligible weight. And furthermore, what we're going to assume is that they're free to rotate about around. This is like a string here that's connecting the fish, but also connects the crossbars to the other crossbars. And we'll assume that it's entirely free to rotate without any friction. This is a very reasonable assumption about here and about here, right? So we can have some rotation there, but it's allowed to rotate, but we don't actually want it to rotate, right? So we want, if we want this whole thing to be in equilibrium, right? In rotational equilibrium as well as translational equilibrium, but we'll focus on the rotational equilibrium. So if we want the whole thing to be in rotational equilibrium, that would mean that this part has to be in rotational equilibrium, right? These two fish and this crossbar has to be in rotational equilibrium. And then the bigger part here, this would have to be in rotational equilibrium, right? And like if we were to kind of, let's say that we go through the process that we'll go through this is we'll say, all right, this has to be in rotational equilibrium here. And then we can pretend like this is just one entity. And then this would have to be in rotational equilibrium here, right? And then we can pretend like this is just one big entity, and we would need this whole thing to be in rotational equilibrium as well, right? And so we have several pieces that must be in rotational equilibrium. And what we'll do is we'll just start with the innermost piece, and we'll say, right, what do we need to make that in equilibrium? And then we can work outwards from there. So let's do this. Let's do a free body diagram of this lower bar here. So free body diagram of the bottom bar. Here's the bar, and we have, here's C, right? This is the weight of C, and the weight of D, I'll just call them, instead of W, I'll just call it C and D, something like that. And then there's going to be this string, right? There's some force in the string that pulls it up. This is what's going to keep it in translational equilibrium. I could do, some of the forces in the y direction. I would see there here that F, the magnitude of F, has to be equal to C plus D, right? But that's we'll build on that later. So in order to find out how C and D need to be related, and actually let's go ahead and say this is 2 inches here, and this is 7 inches here. And this is the symbol for inches, right? That's inches, two little hash marks, a little 10. Or feet is like, that would be 2 feet, just one mark there. So, all right, there's an infinite number of points we can take the sum of the torques around to have rotational equilibrium. I could, take the sum of the torques around here, or I could take it around here. But the most convenient place is probably going to be right here. If I take the sum of the torques around here, I don't need to include F. And this is actually my most complicated force because it's both C and D together, right? It's C plus D. So if I just take some of the torques around here, kind of just draw, here's where my origin is, X, Y, positive torque would be counterclockwise. I'll take the sum of the torques around that point. Let me just call it, point P. So doing this, we'll take some of the torques around point P. This is going to be a counterclockwise, right? So we have, this is 7 inches times D. And then this is going to be clockwise, so minus 2 inches times C equals 0, right? And I get this relationship here. I can say that we have C is equal to 7 halves of D. So at least I know, I don't know what C or D are, but at least I know the relationship between them. And that's a start, right? Of course, then I have one equation, two unknowns, so we can come up with another equation. If I did sum of forces in the y direction, just kind of, I mean, we could, and that might be the way that we initially start out, summing the forces in the y direction. This is going to be F minus C minus D equals 0. And so we'd say here F is equal to C plus D. That doesn't actually do us a lot of good. It did give us another equation, yes, but it also introduced another unknown. So we still need another equation. So similar strategy to what we've employed in the past with just Newton's laws and free body diagrams, things not rotating. We said I can get another equation if I do another free body diagram. This is what we discussed as our general strategy. So let's do a free body diagram of this middle bar now. And I'm going to treat this all as one force. This is C plus D, right? We actually said F was C plus D. And if it pulls up on this lower bar, it pulls down on the middle bar, right? Action-reaction pairs. And then I can free body diagram this middle bar, right? And that'll give me another equation. And at first it might seem like it gives us another unknown, but it actually, we know B. So we'll be able to solve things. So free body diagram of the middle bar. We have looks like this. We have C plus D over here, and then we have B over here, which was 27 ounces. Just leave it as 27 ounces. And then we had another force up here, F2 or something. The dimensions, this was, let's see here, 6 inches on the left, 2 inches on the right. 6 inches, 2 inches, and let's do the sum of the torques around this other point, which I could call point P, but just for clarity, I'll call it point 2, P2. So sum of the torques around P2. This is going to be, again, we have counterclockwise with the C plus D, so we have 6 inches times C plus D minus 2 inches times 27 equals 0, right? And so then we can say here C plus D, just solving, C plus D is equal to 9. This comes out to 54 divided by 6, right? So this is equal to 9. But remember, C is 7 halves D. So we say here 7 halves D plus another D is equal to 9. So this is 9 halves D equals 9. So then D is equal to 2, and our units there were ounces, right? So fish D weighs 2 ounces. And then actually, we can find C now, because C is equal to 7 halves of 2 ounces. So that's equal to 7 ounces is equal to C. And we're just able to solve things quickly now. So fish C is 7 ounces, fish D is 2 ounces, and we still need to know fish A, right? So what we can do to find fish A is we'll just free body diagram the whole thing here, where this coming down here is going to be fish B plus C plus D, right? So free body diagram of the top bar. We have fish A. We have here B plus C plus D, which is, what is that, 27 plus 2 plus 7, is that 36? 36 ounces. This is force 3 up here. These dimensions, this was 12 inches. This is 3 inches. And so we end up here, which actually, let me kind of shortcut this one a little bit. These are equal direction, opposite sides. So this one causes rotation that way, this one causes rotation that way. They have to balance out. So their force times their moment arm has to balance. So we can actually do this one much more quickly than writing out the sum of torques. But it's still a very good habit to write out sum of torques about, call this 0.3 now, equals 0, and write out all of these. Maybe I'll do it anyway. So we end up here, well, this implies that we have 12a is equal to 3 times 36. That's what it comes out to. So this force times distance equals this force times this distance, balancing out. And so then we see that A is equal to 9 ounces. And there we have it. We have the weights of all of these fish to balance the mobile so that we can build a fish mobile for our children. Since we have all this time now in isolation.